topic will be the application of machine learning for atomic force microscopy images. So the general outline that first I will just introduce what is the overall problem of what we're trying to do. Then I will go a bit more detail into how atomic force microscopy works, and then for machine learning, and then finally we'll go to the results and then draw some conclusion of the current results and see what we can do in the future. So to begin, atomic force microscopy, or AFM, is this method of microscopy where you can image very small and sensitive structures using this kind of very sharp tip that is attached to a cantilever, which when you bring it very close to a sample that you're imaging, then there will be some force interaction between at the very end of the tip and the sample, and then this causes some kind of change into the position or the motion of the tip that can be measured, and then you can actually obtain very sharp images of the sample. So one of the pioneering experiments for the very high resolution AFM is this one from Cross and others from a bit over a decade ago, where they imaged the benzene molecule, which is this 5-carbon ring structure, and you can actually see the whole molecule in very high detail in the image. And there are lots of other great experiments of imaging some organic molecules and characterizing some chemical on-surface chemical reactions in many experiments. Of course, not all this well in the world. There are still some challenges. One of the major challenges with AFM today is that most of the experiments are still conducted on samples that are fairly flat. So, for example, for this bromodichlorobenzene molecule, the AFM image corresponds rather straightforwardly to the geometry of the molecule. But if you got something more complicated, like the 1s camphor molecule here, then it's much harder to go from the AFM image back to the structure that you're actually imaging. So we're hoping that we could address this problem and perhaps others using machine learning. So in the recent decade, machine learning and this deep learning in particular has really made big waves across science and the society at whole. I just picked up a couple of examples. So, for example, in computer vision, like image classification, image segmentation, and generating images, there's been a lot of advances in the recent decade, and there's been a lot of advances in like reasoning and playing games like Go. Recently, the machines won the best human players. There's machine translation, and at the very end of last year, there was this really hyped result from Google's DeepMind team of this AlphaFold 2 model, which was deemed to have solved the difficult challenge of protein folding in biology. So the kind of things that we're hoping that we could address with machine learning here is can we recover the geometry of the sample from the AFM images, even these more difficult cases? Could we get some more accurate chemical information like the electrostatics or the elements? Sorry, this thing is blinking. Okay. So even in this flat case, for example, we don't exactly know like which one of these atoms here is the chlorine and the bromine. So these kind of things could be interesting to know. And of course, automation, like in machine learning in general. If you can do something with less effort and quicker, then that's better. So going to AFM, it bit more in detail. So again, we got this very sharp tip that is in some kind of force interaction with the sample. And here we will focus on the so-called frequency modulation, or AFM, where the tip is actually oscillating above the sample at some specific amplitude, and then the interaction causes a change in the oscillation frequency. So the wiggly line here is just like illustrating that when we're like far from the sample, then we get some frequency, and when we're close, then it changes. Another important trick in the very high resolution AFM imaging is this idea of attaching an additional particle like the CO molecule to the very end of the tip. And the idea here is that the CO molecule, for example, is flexible, so it will bend around the sample when you go close, so that you're not disturbing it too much. And it's also chemically inert, so that it doesn't react with the sample, or the sample doesn't like jump into contact with the tip. And then if you do your scan across whatever sample you have, then you can obtain this very sharp contrast of the sample that you're imaging. And depending on the distance that you are, then you get a slightly different contrast. Now, for the application in machine learning, one of the difficulties with AFM is that it's not a high throughput method, so it's difficult to create very large databases of experiments. So what we do instead for training the machine learning models is to use simulations, and we do the simulations using this so-called pro-particle model. What the idea is that you have this so-called pro-particle, which is modeling this soft particle at the apex of the tip, and it has force interactions with the sample through the Lennard-Jones potential, which is very often used in this kind of atomistic simulations, and the electrostatic interaction through the Coulomb potential with point charges on each of the sample atoms and the probe particle. And then the probe particle interacts with the tip using spring force, which has two components, a radial component. So how far is it from the tip, and then the lateral. So how far is it from the like equilibrium position below the tip. So the idea here is then that you've got your molecular geometry that you're simulating, then you scan over the geometry, and at each position you start at some distance, and then you approach the geometry, molecular geometry, and you let the particle relax around the sample as you approach, and then this gives you all of these trajectories for the probe particle and the forces that it experienced across those paths. And then there exists this theoretical formula that you can use to integrate over these paths, and then you will obtain this frequency change that you would get in an actual frequency modulation AFM experiment. And the model is reasonably accurate. So, for example, for this pentazine molecule, if we compare the experiment to the simulation, we can see that it matches pretty closely. and it's also very fast. We have a GPU implementation where we can do like on the order of like dozens or up to like 50 simulations per second, which allows us to create this large database of samples very quickly. Then going into machine learning. What is machine learning? Well, like going back to the sort of like traditional programming, we're usually like just thinking algorithmically that we are programming some predefined steps that we apply to some data that we are given. But in some much more complicated tasks like computer vision, and then it gets really hard to actually code these predefined steps. So what we might want to do instead is to just give some examples of the task to the machine, and then hope that it learns to do the task based on those examples. So the goal is to learn some task without explicitly programming the program to do the task, and usually machine learning is considered to be a subset of artificial intelligence for this reason. In practice, what we do is just function fitting, and then the like general procedure in the supervised case, there are lots of different kinds of machine learning: supervised, unsupervised, active, and reinforcement learning, for example. But in like the simplest case, what you do is first you gather some database of these input-output pair samples that like are examples of the task that you want to perform. So like the classic example is classifying images based on whether it contains cats or dogs. So then you have a database of images, and the input is the image and the output is the answer. Is it a cat or is it a dog? Then you propose some kind of function or model which then takes in these inputs, these images, for example, and then output some answer. And then importantly, this model function should have some parameters that you can tune. So when you change the parameters, then the output changes on a given input. And then you feed the parameters to the database so that the model gives the correct answers as often as possible. That's like the simplified version of what is machine learning. Of course, in practice, there's a lot of difficulties in each one of these steps. So, for example, in our case, even gathering this database is quite difficult. So we had to resolve the simulations, and for these functions, there are a lot of options to choose from, and then in the feeding the parameters, there are many different algorithms. So there are some that are used more often, and then just even defining what the correct answer means is not a trivial task. So even though we say that the program is like learning the task, and in practice, like most of the intelligence is maybe in the brain of the engineer that is making the model. So here we will consider a specific class of these model functions called the artificial neural network. Usually, these networks are visualized as these kind of networks of so-called neurons that have, which are like grouped into these layers, and between each layer there are lots of connections between the neurons. So the kind of structure of the network is reminiscent of this like biological neural network. So that's where the name comes from. So your data enters in at the left side as some kind of vector, and then it gets transformed into another vector. And the way that that happens is that first you take in your vector, you multiply it some matrix of weights, which is like the parameters of your model, plus some, usually you add also some constant vector there. So that is just a linear transformation of the vector. And then you apply some function g, which can be any nonlinear function, which is usually called the activation function of the layer. Without going into too much details, the two activation functions that we use here are the ReLU and the Ligerelu functions, which are basically like these piecewise linear functions. And I probably should add some kind of graph here. So the ReLU is just a flat zero on the negative side, and then is like just outputs the input on the positive side, and the Ligerelu is almost the same, except on the negative side it has some non-zero value. So this alpha value usually has some very small value. And then your neural network basically is just, you stack a whole lot of these layers together, and then somewhere at the end comes an output vector, which is the answer to the question that you're asking. And the number of layers and the sizes of each layer are like hyperparameters of the model, which is to say that you decide and you try a lot of different things to see what works the best. So then fitting the parameters, which would be these weight matrices in the neural networks, the first thing that you need is a loss function, which is something that tells you how bad is the prediction of your model for a particular example. So it's it outputs some number which is bigger, the bigger the error. So an often used loss function is the mean squared error, where if y here is the prediction of your model and y tilde is the reference output that it should give, then you just take the difference of each element of the output between the prediction and the reference. You square the difference, and then you sum over all the elements and divide by the number, so you're taking the average. So it's easy to see that this is 0 if and only if the prediction is exactly equal to the reference answer, and if it's not, then it's something bigger than 0. And then the most often used algorithm for then fitting the parameters is the so-called gradient descent, where the idea is that you take the gradient of the parameters in your model with respect to the gradient of the loss function with respect to the parameters in your model, and then you step in the direction opposite to the gradient. So the idea is kind of that you're going downhill on the loss function, so that you're trying to minimize the loss function. So that if we imagine, for example, that w here is some parameter in the model, then we update the parameter by taking the previous value of the parameter and then just subtracting some amount of the gradient. And here eta is the so-called learning rate, which just is hyperparameter that decides how big the steps are. And there are lots of variation of the gradient descent algorithm, which we will not go into here. In neural networks, there's this specific algorithm called backpropagation, or backprop, which performs this gradient descent. And the name comes from the fact that because neural networks are a function composition, then you calculate the gradient using the chain rule of differentiation, starting from the end of the network and then going backwards. Then overfitting. Because these neural networks often have a lot of parameters, then you might have to worry about overfitting your model to the training samples, which is to say that even though you get a low value of the loss function on the samples that you train on, then if you go outside your training example, so if you get a new data point, then your model actually doesn't perform so well. So for example, here is just an example of some data where the true function is a quadratic function, and then you have some samples which have some noise, and then you have a fit which works fairly well in the region of the data that you have, but then if a new sample comes in that is outside the range, then your fit like completely fails. So in this case, the model was over-parameterized. But if you choose the correct number of parameters, then you can get a good fit even into noisy data. And the way that you usually kind of monitor and test if your model is overfitting is that you split your training or your data set into several different sets. The training set, which you use to fit the model parameters, and then validation set, which is used for testing all the different type of parameters or different like versions of your model, and then finally test set, which is the final test on how well your model performs, and you don't fit any parameters to that set. In neural networks in particular, there's this thing called dropout, which is often used for trying to prevent overfitting. So it's pretty simple that if you take some layer in your model and you apply dropout into it, then you just during training just randomly zero out some of the neurons in that layer. Then going into convolutional neural networks, and these are the type of neural networks that are often used in this computer vision or any task that has some kind of like image or any data that has some kind of spatial structure where we can actually order the data. So this is a sort of an example of what a 1D convolutional layer might look like. So imagine that here we have some input vector of data, and importantly, these elements in the vector are now in some specific order so that we couldn't, for example, exchange these two. Then the way that we get an output in a convolutional neural network layer is that for each element in the output, you only consider some local subset of the input. So in this example, we would have 3 connections entering each element in the output, and then the similarly colored connections denote shared weights, so that you use the same weights for each position. So you can see it kind of as sliding a filter across the input, so that you always take subsets of 3 elements in the input to get each element in the output. Then in the 2D case, which would be like the images, you can think that your filter is some kind of like you could say a small image that you kind of slide across the input, so that at each position you take the corresponding elements in this grid, and then you multiply them together and then take the sum, so that then you get some kind of transformed image from the like the convolutional operation. And typically you would have multiple different filters in each layer of this kind of network that would like pick out different features in the data that you have in that layer. Another important building block of the convolutional neural network is the pooling layer, which is used to summarize the data, like the local regions in the data. Too often used pooling layers are the average and max pooling layer, where you take some local neighborhood in your image, say, and then you just take the average over the elements in that neighborhood, or maybe the maximum, so that you reduce the size of the data. So then the general structure of a convolutional neural network would be typically that you have a whole bunch of these convolutional layers, and then you have some of these pooling layers in between. So for example, this VGG16 network is one of the well-known image classification networks. And the general intuition is that is often given for this kind of why these networks work is that the first layers kind of pick out some very simple features in the input image, like some edges in some specific directions, and then it moves gradually into some more abstract features, like picking maybe it's some part of the network recognizes that there's a tire of a car in this part of the image, and then the later layers then use that information to decide that okay, there's a car in that image. Or that's a story anyways. In practice, it's very difficult to assign any kind of specific meaning to the individual parts of the network, and there have been shown some of these cases where the network is actually looking at completely different things than what a human would while doing the same task. So for example, in this example, they gave one of these image classification networks first an image of the skin of an elephant, and it recognizes this is an Indian elephant. Give it an image of a cat, it's a cat. But then you give it this kind of really weird image where it has the shape of a cat, but the texture is one of the elephant skin, and it definitely thinks that this is an elephant. So in this case, the network was biased towards looking more at the texture that is present in the image than the shapes, which is probably more what a human maybe would look at while looking at an image. And the final thing that I would like to introduce about this neural network is this idea of this fully convolutional neural network. So in this previous example, the size of the features in the network were gradually just reduced to smaller size so that finally the output of the network is just a vector. But there's another option that you could also output an image from the network, and then there's this one quite very often used type of network called the UNet, which is this kind of fully convolutional neural network. So it does kind of similar thing as the classification networks, that it reduces gradually the size of the features in the network, but then it actually goes back up, so that it uses some kind of upsampling and more convolutional layers to put the image back into the size that it came in at. And this is often used in tasks, for example, like image segmentation tasks, where you want to divide your input image into some kind of regions where there's something important that you want to look at. Okay, so then going back to our specific case of application, the Academy Force microscopy images. Let me just take a quick drink. So now the question remains, like, what should our network output? And the thing that we're interested at is these molecules. So the first thought might be that why not just have like a list of coordinates of each of the atoms in the molecule? But this turns out to be rather difficult for several reasons. One is that it's kind of the coordinates are kind of moving target, in that if you like translate your molecule geometry, then the target output would become completely different, even though like the overall structure is pretty much or is the same. It's just at a different position, and then although different molecules of course have different number of atoms, then your target would have a variable size, which is also a difficult thing to deal with. So this is not the answer, or at least it's not the easy answer. So what we have done instead is to use this kind of fully convolutional neural networks where the output is also an image, which in some way describes the information in the molecule that we are interested in. So we have designed several of these kind of image descriptors. First one is the one that we call these van der Waals spheres, where each atom in the molecule is represented by a sphere, which is proportional to the van der Waals radius of the elements of the atom. So that then you have this projection where the brightness indicates how close the atom is in the image. So this is a quite intuitive descriptor of the molecular geometry. Like if you just like compare this image, you can see that you have all of these atoms in the descriptor. The one thing to note that not all of the atoms are present. So for example, we have some like deeper atoms inside the molecule which are not present in the image, and this is because AFM is not a method that could like penetrate inside the sample. So we don't ask of the machine learning model to predict something that it really can't know. The second one is the atomic disks, which has a fairly similar idea, except that the atoms instead are represented by these small disks, which are like conically decaying from the center position. And again, the brightness means that it's closer. So this like attempts to like more accurately pinpoint the exact locations of the atoms. Then there's the height map, which is an isosurface of the force, of the vertical component of the force field between the sample and the tip. So it's a kind of more combined. It represents some more combined information of the atoms in the molecule, and it's especially interesting in relation to the last descriptor, which is the ES, or the electrostatic map, which is the vertical component of the electrostatic field of the molecule. so that if you combine with the height map, then you get this like three-dimensional representation of the charge distribution around the molecule. So blue here, for example, would mean that there's more electrons at this position, and red that there's a depletion of electrons in that position. Then the architectures of the models that we use. So like I said, these are like these fully convolutional neural networks. So the input is actually a set of AFM images taken at different distances, a total of 10 different images. Then they enter the network. There's alternating 3D convolutions with these Ligerelu activations and average pooling layers that gradually reduce the size of the feature maps. And then they go back up in 3 different branches, which each output a different descriptor. So for this first model, the outputs are the atomic disks, the vulnerable spheres, and the height map, which roughly would say that characterize the geometry of the sample. So in each one of these output branches, we have at each stage a nearest neighbor upsampling followed by two 2D convolution layers, again with Ligerelu activations, and then it gradually goes back up to the same size as the input, which then finally outputs the descriptors that we want. And then the second of the two models to use is the one that we call the ES electrostatic model, because it's predicting the electrostatic map along with the height map to give this kind of 3D representation of the charge distribution. So the input here is a bit different from the last case, that there's actually two. So the two different AFM images are taken off the same sample, but using different deep functionalization. So different particle at the end of the deep apex. So for one we use the CO molecule, and the other one the xenon molecule, and I will explain in a minute why we do that. But the overall architecture of the model is fairly similar to the last case, except that in this case we also have this kind of skip connections from this unit architecture in this model, where the idea is that you also provide the information that it's what's present closer to the input, also at the end of the network, because some of the details could easily be lost in the very deep network somewhere in the middle. So why two tips? Because we are trying to predict the electrostatic field around the molecule. Then there's been some previous studies which have shown that if you image the same sample using two different tips, then you get a very different image, which has this kind of different distortions of the molecule. So for example, the xenon tip has a slightly positive charge, and the CO tip a slightly negative charge. And there are also other factors, but the charge of the tip is one of the main contributors to the difference between the images. And this study from Hapala and others show that they could actually extract this electrostatic properties of the molecule by mapping these differences between the two different images of the two different taken with the two different tips. So we're hoping to use this same idea to advantage in this model, so that the model could learn why the two images look different in order to like extract then the electrostatic properties from the images. Then finally going to the results. So first for the geometry predictions using first of the two models that I just introduced. So we train the models on simulations again, and then here we are also testing first for the simulations. So here's an example of a particular molecule taken from the test set. So the input is again this set of 10 AFM images. And then here we have the prediction for the atom disks, van der Waals spheres, and the height map descriptors. And then we compare to the reference solutions that we can compute from the molecule geometry. So overall, we could say that the prediction is very close to the reference in all of the cases. So we get like the overall shape is correct, and then the like brightness contrast is very close to correct. Some of the difficulties are that the prediction is a bit more blurry than the reference, which makes it a bit harder to distinguish exactly where the atoms are, and also some of the deeper excuse me, some of the deeper atoms in the molecules are not predicted as well, but overall it's very good. And here's another example which kind of exemplifies how this maybe could be useful. So we have here this kind of molecular geometry which is very flat, but it's kind of at tilt, which makes the AFM images very difficult to understand. But the model prediction quite clearly shows this kind of carbon ring structure that the molecule has. And again, the prediction is a bit blurry, but overall it's very good. Of course, the simulations are not what we're aiming at. We would like to also test this on experiments. For experiments, we of course then have the difficulty that we don't have this kind of reference solution, especially in this kind of more 3D cases where it's difficult to know what you're even looking at. But what we did instead for the experimental validation is to try to find the adsorption configurations of this 1s camphor molecule. So in this image, each one of the rows corresponds to one experiment that we have of this molecule. And on the left side, we have the experimental AFM images. So what we do then is to make the prediction of the van der Waals spheres descriptor from the experimental images, and we chose this descriptor in particular because we found it to be like the most robust and still give like the most detail in the prediction. Then we try to find what is the configuration of the molecule in this experiment by comparing the descriptor into the reference descriptors that we can get from just computing from the molecular geometry that we know that the molecule has. So then we take a whole bunch of these different configurations and then compare the predictions using just simple cross correlation, which allows us to find some good matches between the simulation and the experiment. And then we can also simulate the AFM images from this the geometry that we have for each case. So then at the end we can compare the AFM experiment to simulation in each case, and we find that for the most part, the match seems to be quite good. So this at least shows that the predictions from the model, even on experimental images, give something reasonable out. Then go into the second model, the second task of predicting the electrostatics from the AFM images, and again starting with simulation examples. So here we have chosen 3 different examples from the test sets. So again, the model in this case takes 2 inputs in, the CO and the xenon images for the same sample. And then comparing the predictions to the reference in each case, we can see again that it does very well on the simulations, so that the overall contrast is very similar. Some of the more like closer to neutral regions, which would be like white here, are a bit more iffy, but overall very good. In this third case, we can also compare an earlier experimental study using Kelvin probe force microscopy, which is a method which can be used to map this kind of electrostatic properties, or the electrostatic field, which is the same quantity that we have in the descriptor here. So in this study from Schuller and others, they found this kind of contrast for the electrostatic field around this molecule, and we find that in our prediction and simulation case, the contrast is very similar. The only big difference is that there's kind of these positive regions around the sides of the molecule, which are not present in this one, but in this case, or in our case, we map the electrostatic field on a 3D like contour that goes like around the molecule. So here we are actually looking at the side of the molecule, with, but in this case it's like a constant height measurement above the molecule. So that is probably the reason for the difference. Then for experimental predictions, which is like the real test case, we have 2 different experiments. First one is for this bromodichlorobenzene molecule, where we have obtained both the CO and the xenon measurements of the molecule on a copper surface. So we can, in this case, compare the simulation to the experiment, because we have fairly simple geometries, so that we can actually know what it looks like. And overall, we see a fairly similar pattern, that over these halogen atoms, the chlorine and the bromine, we have a negative charge, and then in between, around the hydrogens, we have a positive charge, which is similar in both the experiment and the simulation. It's just the positive charge is stronger in the simulation than in the experiment, and it's also quantitatively quite good. So we can actually get some kind of like actual number out from the model. So this shows that it's not only like qualitatively pretty good, but it's also quantitatively pretty good, which is quite remarkable, because the like quantitative measurement of the electrostatic properties of molecules using AFM or other related techniques is quite difficult. For the second example, we have this PTCDA molecule. So again, in this case, the simulation and the experimental predictions are quite good. So we have this like positive charge around like the middle part of the molecule with the carbon rings, and then negative charge over the oxygens, and we see a similar pattern in the experiment. Quantitatively, it's not quite as good as if for the other case that it's the predicted field is somewhat weaker in the experiment by about a factor of roughly 2 around the oxygens. And there's also some issue in the experimental prediction where the model actually predicted negative charge in the background of the where there's like no atoms, even though the model correctly predicted that it should be the background because the height map shows that there's nothing actually there. So the robustness of the model could be still improved, but overall the predictions are fairly good. So finally, in conclusion, so we have introduced this machine learning models for predicting the sample geometry and the electrostatic properties from AFM images, and we found that on simulations, which we also trained the model on, it works really great. And then the experimental predictions are also pretty good. There are some issues, of course, that could be still worked on, but it's not too bad. So one of the big questions that we still do have is how accurate is the simulation, because of course we train the model on simulations, but then we want to generalize to a case that is different. So and some of the like differences between the predictions on the simulations experiments probably come from the fact that the simulation, or they do come from the fact that the simulation is not quite accurate enough, and this is especially the case in the very close regime where in the simulation we don't take into account the fact that the AFM tip could actually be like moving the sample molecule on the surface. Those are some of the questions that we still have to address. Looking at some of the future directions, we have like seen a fairly good performance on these very small and simple molecules so far, but we could also, or we would also want to then move to some more complicated molecular geometries. One of the like test systems that we've been looking at recently is this silotetrose, from which we have obtained a lot of AFM experimental data, but in this case it's much more difficult to know what we're actually looking at. So making sense of the model predictions is going to be much more difficult. So this is an interesting challenge. And then we've been also looking at different kinds of machine learning models that we could use. One of which is this graph neural network. So like I mentioned earlier when talking about the descriptors, like the most intuitive model of a molecule would be like that you have these atoms as this set of discrete entities where you can like say that, okay, there's an atom here and it's connected to this other atom. And one way of representing molecule is as this kind of graph. And then there's this new type of neural networks that have been used for learning on graphs. And recently we have been looking at this kind of generative graph models where the idea would be that we take our AFM image and then we iteratively build a graph of the molecule or some part of the molecule that we are seeing in the image, so that on each step the graph would like look at the AFM image and what is the current graph, and then add one atom at a time, and then finally at some point decide that, okay, now it's complete, and we have our complete graph of the sample molecule. Yeah, so this brings my presentation to a close. So thank you for your attention. Any questions, please?
So thank you, Nico. It was 10 minutes overtime.
Okay.
So I mean, I'm not. It was very good on many levels, but I mean, from my perspective, and others can comment, you maybe have to squeeze the methods a little bit.
Yeah.
Just for that, you know. I mean, it's not super strict in the midterm, but 10 minutes over is probably a bit long. And Patrick might, you know, say something else, but I think you could think of that.
Half an hour or 45 minutes. I'm not sure how long.
It's 45 minutes. Okay. So you went to 55. You know, so it's like you can think about that. That's probably like 1 or 2 slides in the methods. You could, you know, I wouldn't like. I mean, the worst thing you could do is like rush the whole thing.
Yeah.
So just think of something that you know just want to spend a little bit less time. I don't know if anyone has a comment what they think is, because I think you could go to the results a little bit sooner, but the results themselves I think were nice. So is there any other comments, like let's say on this side, before we have questions? So is there any sort of stylistic comments? So Andre, you have hand up. Yeah.
Exactly, I agree. What I would personally do was use the description just based on your model, because you don't need to look at different models that were used in the past for the images, and just use what you have really, and then maybe make a just put there yeah, this the structure of a CNN and this thing, or the fully convolutional network. This is a thing you can have in the slides of your own. You can have just the citation of the original papers, but you don't need to explain those and what's the problem. I mean, you can have these slides as a backup somewhere, but from my point of view, at least, it's not necessary, and this will give you at least 5 minutes.
Yeah, that's a good idea.
Okay. Fedor. Yes.
Yeah.
Yeah, minor thing for the, I don't think you have to say anything about it, but you could put the reference for the paper from this year on the slide where you mention it. I mean, this is just more for the,